Hey guys, this video is about acid-base titrations. There are a lot of calculations in this video because that's sort of the nature of this stuff. So if you know, it might be good to take a break every now and then come back to it. But make sure you watch the whole thing because there's some really good stuff in here. It's pretty cool. We're going to start out by defining millimoles, and this is a really nice thing to use when we're doing acid-base titrations, and other times too. So a millimole, as you probably figured out, milli means times 10 to the minus 3, it's just an SI prefix, so 1 millimole is 1 times 10 to the minus 3 moles, just like a milliliter is 1 times 10 to the minus 3 liters. Well, if you take the ratio of millimoles to milliliters, you have 1 times 10 to the minus 3 moles over 1 times 10 to the minus 3 liters. See, the 1 times 10 to the minus 3 cancels, and this is just moles over liters. Guess what? That's molarity, which means we can think about the concentration or molarity of some species called X as being moles of X per liter of solution or millimoles of X per milliliter of solution. Hopefully you'll see why this is really nice as we go through these calculations. So we are going to start out by titrating a strong acid with a strong base. And then after this, we're going to do a weak acid with a strong base and then a weak base with a strong acid. I don't do a strong base with a, well, because I don't start with a strong base and titrate with a strong acid because it's just exactly the opposite of this. So what I have here is the titration of 25.0 milliliters of 0.100 molar hydrochloric acid with 0.100 molar sodium hydroxide. Now these concentrations don't have to be the same. The calculations work out, the same way. But it just makes it a little easier to see what's going on. That's why I set it up this way. So this is the reaction that's going on. Straight acid-base reaction, acid and base. Not in equilibrium. This basically goes to completion. Acid and a base make salt and water. So I'm going to start out. We have 25 mils of 0.1 molar hydrochloric. So I'm going to first calculate millimoles of hydrochloric. See, all I have to do is take the volume in milliliters, which is what we almost always use in chemistry, times the molarity, just thinking about it as millimoles per milliliter. Milliliters cancel. And so we see that we start out with 2.50 millimoles of hydrochloric acid. Now, the equivalence point is the point at which you have added exactly the same number of moles of base as you have acid to start with, which means you've added 2.50 millimoles of base. That is assuming that it's a 1-to-1 mole ratio, which it is here. Let's say it was a 2-to-1 mole ratio. Say we had sulfuric acid, which has 2 acidic protons. Then the equivalence point would be when there's exactly enough sodium hydroxide to use up all of the sulfuric acid, which would be twice the number of moles of sulfuric acid that we start with because we need to pull off 2 protons. But we'll keep it simple. So at the equivalence point, we have 2.50 millimoles of hydrochloric, and it takes 1 millimole sodium hydroxide per 1 millimole of hydrochloric. See, this is where the 2 would come in if it was if there was sulfuric acid, this would be a 2 here and a 2 there. But anyway, we see that we need 2.50 millimoles of sodium hydroxide to use up, exactly use up all of that hydrochloric, and that gets us to the equivalence point. So going kind of backwards, that means if we need 2.50 millimoles of sodium hydroxide, and this is just the molarity upside down, 1 milliliter per 0.100 millimoles, we see that we need 25.0 milliliters of that sodium hydroxide solution. So this is what the graph looks like when you titrate a strong acid with a strong base. These little bumps here, just ignore those. Those are an artifact of my my spreadsheet that it thinks it's going to go up and then it pulls it down. Don't worry about it. This is the data that I used. Volume of sodium hydroxide added. So add about, I calculated about every 2.5 mils. Add every 2.5 mils. I calculated millimoles of hydroxide added. Right. So that would be the 0.100 millimoles per liter of sodium hydroxide. Times the volume, and that millimoles of hydrogen ion left will be what we start with minus what was used. So it would be what we start with, 2.5 minus this number right here. So 2.50 minus 0.25 is 2.25. And this over here is the total volume. So this is the sum of the volume of the the acid that we start with, which is 25 mils, and every time we add some sodium hydroxide, we're diluting it, right? So the volume changes, which means the hydrogen ion concentration changes. This column over here, this is just the millimoles of hydrogen ion that are left divided by the total volume. It gives us the molarity. And, because we know the concentration of hydrogen ion, we can calculate the pH, negative log base 10 of the concentration of the hydrogen ion. And you can see the pH is going up until we reach the equivalence point. That's this point right here. At the equivalence point, all of the hydrochloric acid has been used up, and basically all you have in that solution is sodium chloride, which does not affect the pH in water. So it's a neutral solution, pH of 7. Then, once we get past the equivalence point, if we keep adding sodium hydroxide, now the pH is going to start going up pretty fast. You see this, how steep it is right here? What's happening here is because there's still some acid in here, when we add the sodium hydroxide, it uses up some of the acid, but there's still some acid left, so it pretty much stays, at a pretty low pH. But the equivalence point here is right where we've used up all the acid. As soon as we've hit that point, the pH skyrockets, right? It shoots right up here because now we're just putting sodium hydroxide in there and it's not reacting with anything, so the pH is shooting up. At the equivalence point, this is the inflection point of this curve, which means that this is the exact point at which it goes from being concave up to concave down. If you've had calculus, that means that you know that is where the second derivative is equal to 0. And that's actually useful when you're graphing data on a calculator or a computer. Finding the equivalence point makes it real easy. So let's look at what happens after we've added 10 milliliters of sodium hydroxide. So we figured out, taking the volume times the molarity, how many millimoles we've added. We started with this many millimoles of hydrochloric. We've used up this many millimoles of that hydrochloric because 1 millimole of sodium hydroxide uses up 1 millimoles of hydrochloric. So we have 1.50 millimoles of hydrochloric acid left. And the volume is 35 mils because we added 10 mils to the 25 that we started with, so 35 mils. So the concentration of hydrochloric acid is 0.04285. And because hydrochloric acid is a strong acid, you guys, the concentration of the acid is equal to the concentration of the hydrogen ion, so the pH is just the negative log of this number. So 1.368 or so. So 10 mils right here, about 1.3, 1.4, something like that. So now let's look at after 35 mils of sodium hydroxide has been added. So the equivalence point is at 25 mils. We saw that on the last slide. When we get to 25 mils of this sodium hydroxide solution added, we've reached the equivalence point. This is past the equivalence point. So first we figure out how many millimoles of sodium hydroxide we've added, same way, volume times molarity. And we've added 3.50 millimoles of sodium hydroxide. 2.5 moles, 0 moles of that is used up reacting with the hydrochloric acid. There's no hydrochloric acid left, all gone. And we have left the 3.50 millimoles that we've added, minus the 2.50 millimoles that was used up reacting with the hydrochloric acid, leaving 1.00 millimoles of sodium hydroxide or hydroxide ion unreacted. And so the concentration of hydroxide is just the 1 millimole here divided by the total volume. Again, this 60 mils, guys, this is the 35 that we've added plus the initial 25, so that's 60 mils. And we see the concentration of hydroxide is 0.0167 or so. And so to calculate the pH, the way I like to do it is I get the POH, if I'm dealing with hydroxide, which we are here. POH is negative log base 10 of the hydroxide ion concentration, and then pH is just 14 minus the POH, which gives us a pH of about 12.22. So after 35 mils, right up in here, just a little over 12. That's a strong acid with a strong base. And it's pretty straightforward. Now we're going to look at a weak acid with a strong base. And we're going to show how to calculate the pH at various points along this curve. So the example that I'm going to use to illustrate this is we're going to start out with 40.00 milliliters of 0.1000 molar propanoic acid. It doesn't matter what it's called, but it's an acid. It's a monoprotic acid, weak acid. and we're going to titrate it with 0.1000 molar sodium hydroxide, strong base, weak acid. So this is what the curve looks like. Notice a couple things. The equivalence point, it's not at 7 anymore, it's higher. And you'll see why, because at the equivalence point, what we have left is going to be just pretty much the conjugate base of a weak acid, which is going to increase the pH. Another really nice thing about this, and you'll see in just a minute, guys, is that at any point, once we've started adding some of the base to this weak acid, at any point along the curve up to the equivalence point, up right before the equivalence point, this is a buffer, right? Why? Because what we have is when we add the sodium hydroxide to the weak acid, propanoic acid, we have the salt of the conjugate base of the weak acid and the weak acid. That's what you need for a buffer solution, a weak acid and its conjugate base. So both of these guys are present in solution anywhere in here, which means because it's a buffer, we can use the Henderson-Hasselbalch equation to calculate the pH, which is pretty straightforward. The only thing you have to watch out for, most of the time this will be okay, but you do have to watch out. Remember, the limit on the Henderson-Hasselbalch equation is that we must be able to neglect X, right? In other words, the concentration of, in this case, the concentration of the hydrogen ion must be enough less than the initial concentration of the acid here so that we can neglect it when we do the calculations. If not, then we have to do the full-blown equilibrium sort of calculations. All right, so here we go. Weak acid, strong base. This is the weak acid, propanoic acid. The Ka it ends up for this acid is 1.34 times 10 to the minus fifth. We will need that. Let's see, equivalence point, inflection point, buffer region. Good. All right, so we're going to start out first calculating the initial pH of this solution before we start the titration, okay? Before we add any base at all. So at that point, what's in there that affects the pH is the weak acid. And so there's an equilibrium, like any weak acid, our HA over here, producing some hydronium or hydrogen ion, same thing, and the conjugate base. So this is just an equilibrium calculation. Ka, or K, just equal to x squared over the initial concentration minus x. As long as we can neglect x, then we can approximate it as x squared over the initial concentration of the acid. If we rearrange this, we see that the hydrogen ion concentration, which is x, is approximately the square root of the Ka times the initial concentration of the acid. Once we know the hydrogen ion concentration, pH is just negative log base 10 of that. The only thing is, if when you do this calculation and you get your hydrogen ion concentration, real quick, compare it to the initial concentration, the 5% rule. And if it's not small enough to neglect, then you're going to have to go back and do the full quadratic. Not a real big deal. All right, so here's our reaction. There's our Ka. So at initially, all we do is basically just use this equation right here and this equation right here. So the hydrogen ion concentration is Ka. It's right here. Just plug in right there. 0.1 molar, 0.1000 molar. Square root gives us 1.16 times 10 to the minus 3. Take negative log base 10 of that. And we see that the initial pH is 2.936. Right about there. All right, so that's initially before we add any base, guys. Now we're going to start adding some base. Remember, once we started adding even a drop of the base, right before the equivalence point, it's a buffer, and we can use the Henderson-Hasselbalch. So remember, and when I derived the Henderson-Hasselbalch equation for you, I showed it as pKa equals pH minus the log of the concentration of the base or the acid form. I just rearranged this a little bit to make it more convenient for us, because now what we want to do is we want to use the Henderson-Hasselbalch to calculate the pH. So I just brought the log term over this side, so that's why it's plus. Now, another thing that's nice about the Henderson-Hasselbalch is that because the ratio of this right here of the concentration of the weak base to its conjugate acid, it's in the same solution, it's in the same beaker, the flask. So that means that the volume is the same, which means we don't have to calculate the actual concentration. We can just use the moles, or what we're going to do, millimoles. We don't have to divide by the liters or milliliters, because it's the same and it cancels. It saves us a step or two. So Here's propanoic acid, and I'm going to abbreviate this HPR, so I don't have to write it out all the time. Sodium propanoate. There's a Ka, and we're going to need the pKa because it's in the Henderson-Hasselbalch. So remember, the pKa is negative log base 10 of the Ka. So that's how you get this number right here. You guys should check that. So now we're going to look at after 17 mils of sodium hydroxide has been added. So we started with 40 mils of the acid, and now we've added 17 mils of sodium hydroxide. So what we're doing here is calculating how many millimoles of sodium hydroxide were added, the volume times the molarity. And so we have 1.700 millimoles of the conjugate base, because every time we add one sodium hydroxide, it pulls off a proton from here and makes one of these, the conjugate base. So the millimoles of sodium hydroxide added is equal to the millimoles of the conjugate base propanoate here. So we start out with 4.000 millimoles of propanoic acid, the acid, this right here. And that's just the 40 mils times the 0.1 moles per liter. It gives you 4 millimoles. Minus, okay, because we've added 1.700 millimoles of sodium hydroxide, we've used up that much of the acid. And so there's 4 minus 1.7 or 2.300 millimoles left. We want these numbers because that's what we plug into the Henderson-Hasselbalch. We don't have to worry about calculating the concentration, like I said, because the volumes will cancel. So all you have to do now, really, it's quicker than it took to say it, really. Just to calculate the pH, take the pKa right over here, plus the log of the millimoles of the base form, 1.700, to the millimoles of the acid form, 2.300, and we get 4.742. Okay, so about after 17 mils, it's about right here, 4.7 or so right there. That's the pH. So the pH is starting to go up a little bit, but we haven't reached the equivalence point yet, so it's still saying more or less flat. Okay, now there's a special point, guys, on a titration curve, which is what this is, and that is the point at which the concentration of the conjugate base and the weak acid are equal to each other. Well, the reason that's really nice is because it's going to be in here. If this is the equivalence point, and as long as these are equal concentrations, this will be halfway, right? At that point, when we've converted exactly half of the weak acid into its conjugate base, so the concentrations or millimoles are the same. So what we get in the Henderson-Hasselbalch is pH equals pKa plus log of 1. Well, guess what? Log of 1 is 0. And so that means that at the equivalence point, pH is equal to the pKa. We already know the pKa, so we know the pH. Turning that around, experimentally, the reason that's really nice, this gives us a really easy way to find the pKa for some acid if we don't know it, and that means the Ka. All we have to do is do a titration like this, find the point that's halfway to the equivalence point, which we can with our software, and we'll just read the pH from that, and that gives us the pKa right there. So after 20 milliliters of the base has been added, we have added 2.000 millimoles, which means we've converted 2.000 millimoles of the acid into its conjugate base, propanoate. We started with 4 millimoles of the acid. We've used up 2 because the sodium hydroxide every sodium hydroxide uses up 1. We have 2 millimoles of the acid left. So this ratio, when we plug it in here, cancels. pH is equal to pKa. Not even really any calculations to do. It's just 4.873. We're out there. All right, so that's a nice point. You should remember that. Now, at the equivalence point. So what's happening here, guys, is at the equivalence point, remember we've added exactly enough of the base to use up all of the weak acid. So all the weak acid is gone. It's all been converted into its conjugate base. So what we have in that solution is a weak base, which means that the equilibrium that determines the pH will be that weak base reacting with water, doing its equilibrium to make the conjugate acid and hydroxide. The hydroxide is what affects the pH. This is the Kb reaction for the base. So we're going to need to use the Kb for our calculations here. And remember, Kb, or Ka times Kb equals Kw, so solve for Kb, Kw over Ka. Again, we always assume 25 Celsius unless told otherwise, which means Kw is 1.00 times 10 to the minus 14th. So this is just a regular equilibrium problem. Kb equals x squared over the initial concentration of the base minus x, assuming we can elect x squared over the initial concentration of the base. And x is the concentration of hydroxide and the concentration of the conjugate acid, but we don't care. It's just what we care about is x is the concentration, the equilibrium concentration of hydroxide, and we're at the equivalence point here. That's our x. So rearranging this, we see that hydroxide ion concentration is just the square root of the Kb times the concentration of the base form. So once we can get the hydroxide ion concentration, get the POH, negative log base 10 of the concentration of hydroxide, and then pH is 14 minus the POH. So for our reaction here, with our Ka, at the equivalence point, so remember we started with 40.00 milliliters of 0.1000 moles propanoic acid. So that means because we're adding the same molarity, sodium hydroxide, that means that we've added 40 mils. We have 4.000 millimoles of base added, which means we've used up all of the acid form. The propanoic acid has been all converted to the propanoate. So the concentration of the conjugate base here, we have 4 millimoles of this. The volume here, guys, this is the 40 mils that we started with plus the 40 mils that we added is 80 mils. And so the concentration for this one would be 0.05000 molar. And we'll need the Kb. I'm thinking about this equation right here. What we have here is the concentration of the base form, Kb, Kw over Ka, 7.46 times 10 to the minus 10th. Plugging these in here, we get the hydroxide ion concentration. Easy, right? POH, negative log base 10 of that, and then pH is 14 minus that. So the pH here is 8.79 at the equivalence point. I didn't have room to put the graph over here, but if you go back and look, you'll see that, yeah, it's right at 8.79. All right, so now past the equivalence point. Once we go past the equivalence point, guys, as we add more base, there's no acid for it to react with. So we're just directly affecting the pH and it shoots right up. And then it starts rising gradually again. So we're over in this region right here. So let's say after 47 mils of the 0.1 molar sodium hydroxide has been added. We've added, this is one way to look at it. Because we know it's the same molarity, and we needed 40 mils to get to the equivalence point, we have 47 mils added minus 40 mils of the base used to reach the equivalence point is 7 milliliters of sodium hydroxide in excess that did not have any acid there for it to react with, which means we have 0.700 millimoles of sodium hydroxide in excess, just floating around in that solution, no acid for it to react with. And that's what's going to give us our pH. And so the concentration of hydroxide will just be the millimoles of the base divided by the total volume. And again, this volume is the 47 mils that we added plus the initial 40 that was there is 87. So we get about 0.00805 molar hydroxide. Once more, POH, negative log base 10 of that, pH 14 minus that, so 11.91. 47 mils, pH just under 12 right there. All right. So here's a summary for you guys. It seems like a lot, but once the key to these calculations is knowing what region of the graph you're on. Is it initial? Nothing's been added. Are you before the equivalence point? Okay, so if it's initial and it's a weak acid that we're starting out with and we're adding a strong base, then the pH is just negative log of the hydrogen ion concentration, which is just square root of Ka times the concentration of the weak acid. Once we've started adding the base before the we're up to, but before the equivalence point, it's just the Henderson-Hasselbalch. Halfway to the equivalence point, pH equals pKa, real easy. At the equivalence point, now we've converted all the acid into a base, and so we can find the concentration of hydroxide by just taking the square root of Kb times the concentration of the base form. You saw how we calculated that. And that gives us a pOH, and pH is 14 minus that. And then once we go past the equivalence point, all we have to do is figure out how much of the base is in excess past the equivalence point, divide by the total volume. That'll give us our concentration of hydroxide. Again, pOH, negative log base 10 to the concentration of hydroxide, pH 14 minus pOH. So this is a good thing for you guys to have on your cars probably. All right, so that was a weak acid with a strong base. Now we're going to look at a weak base with a strong acid. In general, titration of any base with an acid, so even a strong base with a strong acid, it's just the opposite really of what we saw before. So if we have a strong base with a strong acid, the pH will start high and go down. The equivalence point will still be at pH 7, but then it'll go down. What we're going to do here is we're going to do the calculations for the pH for the titration of 30.00 milliliters of 0.250 molar potassium hypobromite with 0.250 molar hydrochloric acid. Now this here, guys, this is the salt of the conjugate base of a weak acid. If you replace the potassium with the hydrogen, you have hypobromous acid, which is a weak acid. So this is the conjugate base. We don't care about the potassium. It's a spectator ion. Once this stuff gets dumped into water, it's just floating around. It's not doing anything. So what we have is a weak base, and so we're going to start out at a higher pH, and we're going to go down as we titrate. So I'm giving you the Ka for hypobromous acid, 2.3 times 10 to the minus 9th. And what I want you to do, guys, do this, okay? See if you can figure out, based on what we just did, what pH is before we add any acid. After 12.5 mils of acid has been added, that's the hydrochloric. After 15 mils at the equivalence point, and after 39.75 mils of the acid has been added. So what you should do is you should pause the video here, probably take a little break, do these calculations, try to figure this out yourself, and when you're finished, come on back and we'll go through it together. Welcome back, guys. Let's get started. So before any acid has been added, because it's a base in there, we get the concentration of hydroxide by taking the square root of the Kb times the concentration of the base, right? Kb is Kw over Ka, 4.3 times 10 to the minus 6. Again, this is because we have a weak base. That's all we have in solution. So it's in equilibrium, right? Producing hydroxide ion. So its Kb is the concentration of hydroxide times the concentration of the conjugate acid over the concentration of the base. And it works out like this. So we have a Kb. The concentration we start with, we were told, was 0.250 molar. So all we do is plug into this formula, guys, and we have the concentration of hydroxide initially, which means the pOH is negative log base 10 of that, 2.98, pH is 14 minus that, or about 11.02, right there. Okay, so notice what this curve looks like. It's really just the inverse of titration of a weak acid with a strong base. We start out high and we go lower. Equivalence point is lower than 7 here, right? Same reason. Kind of the opposite though. The reason that the equivalence point for the titration of a weak acid with a strong base is higher than 7 is that at the equivalence point, the only species present that affects the pH is the conjugate base of the acid. So we have that equilibrium of the base producing some hydroxide, which raises the pH, makes that solution more basic. Here, what we're going to have, guys, at the equivalence point, all of the base form will be converted into the weak acid, and so the only species present right at the equivalence point that affects the pH is the weak acid, and it's going to produce some hydrogen ion or hydronium ion, lowering the pH, lower than 7, lower than neutral solution. All right, so this is before any acid's been added. So after 12.5 mils of acid has been added, so we can see that the equivalence point is going to be at 30 mils when we've added, again, it's the same volume of acid added as we started with of the base because I set it up with the same molarities. It wouldn't be the exact, wouldn't be the same volumes if molarities weren't the same, but don't worry about that now. So halfway to here is going to be 15, We're not quite to halfway, but we're definitely before the equivalence point. So that means, hey, we have a buffer solution. We can use the Henderson-Hasselbalch, which is great. So after 12.5 mils of the acid has been added, we're going to use the Henderson-Hasselbalch. We'll need the pKa, negative log base 10 of the Ka, which gets 8.64 for us. And so here, this is calculating the millimoles of the base, the initial base that we had in, hypobromite, B or minus. And this is how much acid we've added. Volume times molarity gives us millimoles of acid, which means that we've converted that many millimoles of the base into the acid form. And so we initially had this many millimoles of the base. We've used up this much. We have this many left. And so that means that the amount of base, so this is the base over the acid form. The millimoles of the base is 4.375. Millimoles of the acid is the 3.125. Just plug in. There's our pKa. Get our pH. Easy as that. So pH is 8.78. Guys, see how nice millimoles are? It's really saves you some work, and it makes things, I think, a little bit easier. Really try it. It's nice. All right, so pH 8.78 after 12.5 mils, right there. So we've gone down some, but not a lot. So 15 mils, this is the point at which we are halfway to the equivalence point. That's really nice because remember, this is where pH equals pKa. And just to make sure, we started out with 7.5 millimoles of hypobromite. We've added 3.75 millimoles of hydrochloric acid. So that means 7.5 that we started with minus 3.75 used is 3.75 millimoles of hypobromite. Same millimoles, same concentrations of the acid and the base. And so pH equals pKa. We're halfway to the equivalence point. pH equals pKa, 8.64, right there. All right, that's not too bad. Now, here we go. Now we're at the equivalence point. So that means we've added 30 mils of our hydrochloric acid. At this point, all of the base, in this case the hypobromite, but whatever the weak base is, has been converted into its conjugate acid. So we have all hypobromous acid. And then that hypobromous acid is what determines the pH, because this equilibrium is what's happening in there. It's reacting with water, making hydronium or hydrogen at hypobromite. So the equilibrium expression, Ka, is x squared over the initial concentration minus x, assuming we can neglect x, looks like this, which means that the hydrogen ion concentration is just equal to square root of Ka, initial concentration of the acid. And once we know the hydrogen ion concentration, pH, just negative log base 10 of the hydrogen ion concentration. So we started out with, again, 7.5 millimoles of hypobromite. We've added 7.50 millimoles of hydrochloric acid, and so we don't have any hypobromite left. All of it has been converted into the hypobromous acid, and so the concentration, before it comes to equilibrium of the acid is just the millimoles over the milliliters. This 60 mils, guys, this is the 30 mils that we started with plus the 30 mils that we added. And so that gives us a 0.125 molar for the concentration of hydrogen ion, for the acid, the initial concentration. So the hydrogen ion is just the square root of Ka times that. So there's our Ka, there's our 0.125 molar. And we see the hydrogen ion concentration is 1.7 times 10 to the minus fifth. pH is negative log base 10 of that, so 4.77 at the equivalence point. So now let's go past the equivalence point. So let's say we've added 39.75 mils. So we're past the 30 mils to the equivalence point. So at this point, the only thing in there, guys, that determines the pH of this solution is the excess, in this case, acid, right? So here we go. We started out with 7.5 millimoles of hypobromite. We added 9.937 millimoles of acid. So 7.50 millimoles of this acid was used up converting the hypobromite into its conjugate acid. So we have no hypobromite left, and the amount of hydrochloric acid that's left is just what we started with, this right here, minus the amount that was used converting the hypobromite to hypobromous acid. So we have this much in excess, and that's the only thing that matters for us right here. We have the millimoles and the volume. Again, this 39.75 mils is the 30 mils of the potassium hypobromite we started with, plus the 39.75 mils of acid that we added. So 69.75 gives us a concentration of 0.0349 molar for the hydrochloric acid. And again, because, guys, hydrochloric acid is a strong acid, the concentration of the acid is equal to the concentration of hydrogen ion. And so pH, negative log base 10 of that. And so we see a pH at 1.46, right about there, just before 40 mils. All right, so that's not too bad. Okay, here's a summary again for you guys for the titration of a weak base with a strong acid. It's just a few things flipped around from a weak acid with a strong base. So initial pH, concentration of hydroxide is square root of Kb times the initial concentration of the base. POH, negative log base 10 of the hydroxide concentration. pH, 14 minus that. Once we started adding acid, before we get to the equivalence point, hey, Henderson-Hasselbalch, same old deal. pKa plus log of the base form of the acid form. Remember, guys, we don't have to actually calculate the concentrations. We can just use some millimoles of each. It's a lot easier. And then remember, halfway to the equivalence point, that's a very special point. We love that because pH equals pKa. At the equivalence point, all of the base has been converted into its conjugate acid, which is what, so the way to think about that, right, is we start out converting all of the weak base into its conjugate acid, and then we let that conjugate acid now come to equilibrium. That's going to affect the pH, and that's why, because it's an acid, the pH is less than 7 at the equivalence point. So at the equivalence point here, hydrogen ion concentration is equal to square root of Ka times the initial concentration of the acid. And yet, you saw how we calculated this when we went through this. pH is negative log base 10 of the hydrogen ion concentration. And then once we get past the equivalence point, the hydrogen ion concentration is just the excess millimoles of hydrogen ion divided by the total volume, and pH is just negative log base 10 of that. So the key to these acid-base titrations, and this is a big deal right here, is knowing, well, what's in that beaker. Okay, are we starting with a base or are we starting with an acid? And then where are we on that curve? Are we at the beginning? Are we before the equivalence point? Are we halfway to the equivalence point? Are we at the equivalence point? Or are we past the equivalence point? Once you know that, then this tells you how to calculate the pH at whatever point you're at. And that's all there is to that, guys.